Hi again, everybody. Here we are, ready for 11.2. Series is the focus of the rest of the chapter. We're going to use the bit that we did about sequences to catapult us into studying series. It turns out we're going to think of series, we're going to find a clever way to think of a series as if it was a sequence, and we can go from there. So probably a good idea first is just to define what a series is as compared to a sequence. Again, if you took algebra, if you remember this stuff, it's the same idea. So a series, think of a sequence, but now add the terms together. It's the sum of the terms of a sequence. So a quick example just to compare the two. Let's go back with that first example I showed you guys at the beginning of 11.1. So a sequence may be 2, 4, 6, 8, 10, ... just a list of numbers. The corresponding series is when you're adding the terms 2 plus 4 plus 6 plus 8 plus 10 and so on. Now this series is not very interesting. You're just adding bigger and bigger numbers. And so the idea will be to find out what the sum of the series is. And really in the end, does the series converge or does the series diverge? This one so happens to not be very interesting because as we keep adding terms, it's just going to get bigger and bigger. This is going to add up to infinity. And so, okay, I mean, it turns out that's not the most interesting case, but that's all right. Just give us an example. You might think, how does this relate? You know, I know we're taking limits maybe, but how does this relate to other things that we do in calculus? And so I made this note here to kind of mention in class, how is a series related to calculus? Well, isn't an integral an infinite sum? Don't you add up all these teeny little rectangles, you know, to get the area under the curve? You're adding infinitely many rectangles, and it happens to be that if that definite integral is finite, then that series, all that sum, even though you're adding infinitely many, it came to a finite value. So there's the connection. And of course, series are very, very helpful just in their own right. But the truth is, we've actually done them before when taking definite integrals. Okay, so here's kind of the beginning of the discussion on, well, then how do we find out what all of those infinitely many numbers will add up to in a series, right? So we can't start with infinitely many. We're going to start with a partial sum, the sum of the first n terms. And we're going to denote that S sub n. Sometimes you see it as capital S, sometimes lowercase s. In any case, S for sum, S sub n. I'm going to use capital S. Okay, so let's take an example of a partial sum. And we're just going to go with, I'll just show you the whole thing. We're just going to go with what we did, you know, our same, you know, kind of simple example. I'm trying to get the camera to get this to be as focused as possible. So I'm zoomed in a little further than how I've been doing it to get the clarity a little bit sharper. Hopefully that's the case. Okay, so what if we had this series way out over here? So now, you know, we have the 2n, we have the formula for the terms of the sequence, but to denote that we're going to be adding them all together, we use the summation symbol from n equals 1 to infinity. Okay, makes sense, hopefully. So if we just look at the first 4 partial sums, okay, the first partial sum, well, that's simply just the first term, right? S1 equals 2. The second partial sum, we're going to add together the first 2 terms. Well, the first term is 2, the second term is 4, so 2 plus 4 is 6 for the second partial sum. The third partial sum, 2 plus 4 plus 6, would equal 12. And maybe if we did one more, 2 plus 4 plus 6 plus 8 would give you 20, the fourth partial sum. Okay, now here's the genius. Look at all of those answers, 2, 6, 12, 20. Think of that like a sequence. The partial sums form a sequence. 2, 6, 12, 20, and so on. If we can find what that sequence converges to, or maybe if it diverges, then we will know what all of these to infinity will add up to. We'll know what that equals. It'll equal a number. Okay, I'll just let that sink in for a moment. If we find the limit of our nth partial sum, if we find the limit as n goes to infinity for the nth partial sum, then that will tell us what all of the infinitely many terms add up to. And more importantly, would it converge or would it diverge? Of course, this one, it's going to go to infinity. We know that, but let's see what happens here. I noted this, at the bottom. So I'm really just saying the same thing, but in mathematical terms. Okay, so I've got my summation from n equals 1 to infinity for my sequence, 2n. I'm going to be able to take the limit of my new partial sum sequence. I'm going to call that S for the sum of the entire thing. If that's finite, then I know my series converges to S. If it is not finite or it does not exist, then my series diverges. Okay. Let's see what we've got for some examples. The question is, does the series converge or diverge? And kind of like back in our chapter on our new integration techniques, the question on the test is just going to be, hey, integrate, right? What happens, right? Kind of similar idea in this chapter. We're going to learn all kinds of different types of series. And the question's simply going to be, does it converge or diverge? Okay, so let's take a look. Obviously, we'll flesh out all those details. So 1 over, I should just begin with the problem, right? So, okay. This one, you notice it's starting at 0. N equals 0 to infinity, 1 over 2 raised to the n. You think, okay, well, where do you even start? Investigate the first several partial sums. I'm trying not to, let me just pull this off the screen so I don't give it away. So if we go through the first several partial sums, well, S0, since we're starting at 0, the 0th partial sum, 1 over 2 to the 0 is 1. The first partial sum, plugging in n equals 0 and n equals 1, would be 3 over 2. The second partial sum, n equals 1, n equals 2, n equals 3, adding together the first 3 terms of the sequence, 7 over 4. Feel free to check these if you desire. And I go, okay, so we're kind of looking for a pattern. The truth is, let's get one more. I think that'll be enough. The third partial sum, n equals 0, 1, 2, 3. Add all those together. It's 15 over 8. And then I'm going to write that as a new sequence down below. And you notice I write the 1, the very first one, as a fraction. 1 over 1, 3 over 2, 4 over 7, 15 over 8. And okay, there's our sequence. Now we have to figure out a pattern to describe that partial sum sequence. Okay, so not easy. Good thing we've got some practice with these. We notice that it's a fraction, so that's helpful. I can think of the numerator and denominator separately. Maybe we start with the denominator. 1, 2, 4, 8. And this came from 0, 1, 2, and 3. And you might quickly realize, oh, that's 2 to the 0, 2 to the first, 2 to the second, 2 to the third. From n equals 0, 1, 2, 3. And that's exactly what's going on. It's actually just that denominator right there, 2 to the n. Turns out to be the denominator after you've added the terms. And you can see that while you're adding, right? The 2, the last denominator, always, that's the denominator of the whole thing. Okay, so the denominator will be 2 raised to the n. Well, then what's going on with the numerator? And that's a lot more difficult, 1, 3, 7, 15. But maybe, after a lot of staring, you notice that the numerator is actually connected to the denominator. It's not so obvious for the first one, but 2 goes to 3, 4 goes to 7, 8 goes to 15. If you double the denominator and then subtract 1, you'll get the numerator. Again, double the denominator and you'll get the numerator. It even works back here, 2 times 1 minus 1. Right, that still works. So here's how I'm going to describe it. The nth, if we think of the sequence, S sub n, or the nth partial sum, I should say. So my denominator is going to be 2 to the n. My numerator is twice that minus 1. And my notes here tell me think about this first, and then I'll think about the numerator. That's kind of okay. All right. So once I have that formula, then I'm going to take the limit, and kind of off the screen here. I'm going to take the limit as n goes to infinity. Okay, and so I'm thinking, what is this? What do all these add up to? So it's the limit of my nth partial sum sequence. And you notice I have simplified the numerator. 2 times 2 to the n is 2 to the n plus 1. And now I notice there's a mistake. This should be a minus, not a plus. Turns out that's not going to change my answer, thankfully. My mistake there. Okay. So I've got my nth partial sum limit as n goes to infinity. And then the tricky part here is recognizing that I should split that fraction like so. 2 to the n plus 1 over 2 to the n minus 1 over 2 to the n. These cancel very nicely down to 2. And I'm subtracting my 1 over 2 to the n. If I take the limit as it goes to infinity, well, 2 minus 0, right? And my answer here for that limit is 2. And so I know that's what my original series is adding up to. If I add all of those infinitely many numbers, the more terms I add, the closer it gets to 2. And so this series converges to 2. And we can kind of see that back here even. Right? Just the first term is 1. But as I keep adding, they get closer and closer to 2. right? That's just an eighth off. If I did one more, you know, I could see it getting even closer to 2, but not quite there. The more terms I add on, I get a little bit closer to 2 every time. And there we go. Okay, that's gonna be it for the first part of this conversation. See you for part 2 in the next video.